Okay. So, the last prerequisite that you need for understanding things in this course is this complex arithmetic and complex numbers. I think most of you would be familiar with this, but still it is good to revise what these what complex numbers are. Now, complex numbers are a pair of real numbers and they are usually denoted a plus j b, and this j is actually square root of minus 1. Okay. And a and b are real numbers. And one can plot this on the complex plane if you like. Okay, so you can have the real part here, imaginary part here, and a plus j b is just a here and b here. Okay, it is exactly like the two-dimensional plane, it is complex plane. Now, addition and multiplication are easy to see. A plus j b 1 plus a 2 plus j b 2 is simply going to be a 1 plus a 2 plus j b 1 plus b 2. It's quite easy. Multiplication is also quite easy. You simply use the fact that j square is minus 1. Okay, so if you do that, you will get a 1 a 2 minus b 1 b 2 plus j a 1 b 2 plus b 1 a 2. Okay, so you just multiply term by term and group the terms together, you will get this. And the other little trick you might want to remember about complex numbers is inversion. If you want to do 1 by a plus j b, this you have to multiply by complex conjugate, which is a minus j b, and if you do a plus j b times a minus j b, you get this magical cancellation of the imaginary part and it becomes real. So, you simply get a minus j b divided by a squared plus b squared. So, which is just a by a squared plus b squared minus j b by a squared plus b squared. Okay. So, a minus j b is called the complex conjugate of a plus j b, and if you multiply a plus j b and a minus j b, you get a real number which is a squared plus b squared. Okay. So, this is basic complex numbers. The most important thing to know, I guess, in this course is this complex exponential. Okay. So, just like we looked at e power x for x real, okay, one can look at e power z where z is complex, as in z is let us say x plus j y. Okay. And if you look at e power z, it is e power x plus j y, and that is nothing but e power x times e power j y, and it turns out this type of an expression has a very simple simplification. It turns out, and this you might want to remember, e power j y is cos y plus j sin y. Okay, so, this is a very important identity that you should know as part of this course. E power j y is cos y plus j sin y. So, once you write that out, this simply becomes e power x cos y plus j e power x sin y. Okay, so, this is the definition of the complex exponential. Okay, and it is very crucial, and it will show up again and again in this class. So, for instance, a very commonly seen exponential is e power j 2 pi f naught t, and this you will see is cos 2 pi f naught t plus j sin 2 pi f naught t. Now, we might wonder, everything that we deal with in real life is real, of course. I mean, all the voltages and currents are real. Why do you need complex numbers? Okay, so, usually in analysis, complex numbers are much easier. So, for instance, by the same argument, why did we need complex numbers at all in the first place? If you remember why we needed it, there are quadratic equations for which there are no solutions in the real numbers. For instance, x squared plus 1 equal to 0 has no solutions in the real numbers. On the other hand, if you imagine that there is a complex root, then you get nice answers. Okay. So, likewise here, the complex signals are useful in solving for real circuits as well. You will see it's very powerful, and it gives you wonderful transform ideas, etc., and it simplifies a lot of the analysis if you use the complex exponential as opposed to the real exponentials in real sinusoids in many cases. Okay. And this identity is quite important, and you can see that the real part of e power j omega naught j 2 pi f naught t is actually cosine 2 pi f naught t, and the imaginary part is sine 2 pi f naught t. Okay. So, these are important identities which you should be comfortable with, and it will show up quite often in this class. Okay. And the other thing about complex numbers is the polar form. Okay. So, if you look at a complex number a plus jb, one can write it in the polar form, which involves the radius r and the angle theta. It turns out if this radius or the distance from the origin to a plus jb is r, we know that r squared is a squared plus b squared, for instance, and we also know that this coordinate is a and this coordinate is b, which means b is r sin theta and a is r cos theta. Okay. So, a plus jb is the same as r cos theta plus j r sin theta, which is the same as r cos theta plus j sin theta, and what do we know is cos theta plus j sin theta is r e power j theta. So, this is called the polar form of a complex number, while this is called the rectangular form of a complex number. How do you go from one to the other? I wrote one equation down, r square is a square plus b squared, and the other equation is tan theta equals b by a. Okay. So, you use these two equations, you can go from one to the other, and there are standard calculations that you can do to go from rectangular to polar form. Okay. And one last point I want to emphasize about the exponential function is the series form, power series form. For the exponential function, e power x is actually 1 plus x squared by 2 factorial plus x cube by 3 factorial plus so on. Okay. So, this series form is useful to remember. In some cases it will show up in some derivations, etc., and it will help you, and there are so many other series that you might know from your school. You might know the geometric series. It is worthwhile knowing the sum of the geometric series 1 plus x squared plus so on for x less than 1 is going to be 1 by 1 minus x. These kind of summations will show up quite a bit, and in general revising series and sequences will also help you in understanding this course. It is not strictly a prerequisite for the course, you might do okay without it, but if you know series and sequences really well, it will also help you. So, the many references that we are giving you have a description of this also, and in a first semester's course in mathematics and engineering, you would have read about series and sequences, and that will also help you understand a lot of the concepts in this course in a very deep fashion. Okay. The last bit of prerequisite that you need is knowledge of integration and differentiation, and I'm not going to talk about integration and differentiation as part of this prerequisites. On the other hand, the material we point you to has a lot of interesting information on that, particularly integration by parts is going to be useful. Various different types of integrations and the formulae for integration will also help you in this class. So, I will encourage you to go through all the prerequisite materials that we have put up on the course portal, and be prepared for seeing the next seeing the real part of the course when it comes to you, and not be surprised by it. The mathematics is not very heavy. I think a lot of the mathematics is supported by a lot of circuits and good examples, and you can quickly grasp what is going on if you spend a lot of time with the examples. But nevertheless, knowing the mathematics well is a great advantage, and you might find the course you might appreciate the course much more if you are comfortable with this basic level of mathematics. Okay. So, with those words, I welcome you to this course once again. Hopefully, you will have a great time learning about networks and systems and appreciating some of the deeper aspects of circuit analysis and system analysis. Thank you very much for being part of this course. I wish you all the best. Thanks.